Hello, everyone. 6 people in the chat. It looks like all my levels are good, but it's always reassuring if someone can tell me that you can hear me. I mean, I see my audio levels going up and down here, but I have been known to stay muted and talking. Um, all right, let me start in the meantime. Um, what you should have watched this week were two videos on 2D kinematics. I didn't do a general theory of kinematics. It's not that useful. Doesn't give you much more than a 1D, the general 1D kinematics. So you did two special cases. You did the case of constant acceleration, which is the situation when things are falling, and constant acceleration due to gravity. And also you did uniform circular motion. Okay, so in uniform circular motion, an object moves in a circle, and it moves at constant velocity in a circle. Later in the course, we'll have the situation where it could speed up or slow down on the circle. But right now, it's the word uniform indicates that it's constant. Okay, so we're going to do two problems. The problem with uniform circular motion, almost all of those problems are really simple. They only take a few minutes. They don't require a diagram. So I'm going to spend almost all of this lecture on the constant acceleration problem. Okay, and so these are also known as projectile problems. This is when you throw something and it accelerates due to gravity. We did that in 1D, but we did it up and down. You throw something up, it goes up and then comes back down. Okay, but now we're going to throw things at an angle, and they'll do this characteristic parabolic path. Okay. And let me see here. Okay, good. I got some confirmations in the chat. Thank you very much, guys. All right, so let's start off with the first problem here. And these are, by the way, very similar to the problems that you'll see on the assignment for next week, and also on the test. And I'm going to do one of them with you, and I'm going to give you two to practice variations on this problem. Okay. All right. So here I go. I'm standing at ground level, and I toss a ball with a velocity of 25 meters per second at 60 degrees above the horizon. Okay, and I'll draw a diagram. I'll tell you what that 60 degrees above the horizon means. And it lands on the top of a hill, which is 20 meters high. Okay, so we want to draw the diagram, and the diagram you should draw in 3 steps, just like you did in 1D kinematics. You should first draw physically the picture you have, then you draw the coordinate system on top of that, and then from that you gather the numbers that you need to plug into the formulas. And these are the initial position, the final position, the initial velocity, the final velocity, acceleration, and time. Okay. For each one of those, well, except for time, but for each one of them, those are pairs of numbers. So if I say what's the initial position, there's actually two numbers associated with that. And so it gets even harder than in 1D to get this right unless you're looking at a diagram and seeing what's going on there. Okay, so let me switch to a whiteboard. I'm going to start drawing the diagram. Okay, and I'll do the first step in black. So there's a ground level here like that, and then there's a hill, and the hill is 20 meters high. I won't draw that in, but later on we'll make use of the fact that that's 20 meters high like that. And the other thing you would see is this is a picture, but it's really it's almost like a movie. Like you'd want to draw the dynamics as the ball moves across the sky. I mean, we can't really draw a movie, but if this is where I am standing on the ground there, and I throw the ball at 60 degrees. 60 is about like that angle there. It goes up, 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 and it comes down and it lands on the top of the hill like that. Okay, so that's what you would physically see. All right, so that's all you need for at this stage. The next thing you're going to do is put down a coordinate system. And a coordinate system, when we say that, we really mean there's two parts to that. There's measurement of position and measurement of time. Okay, the time is kind of hard to draw because, again, this is just like a static picture, not a movie. But you should at least say, where is the ball at t equals 0. Okay, the position being 2D, you need two rulers. You're going to need an x-axis and a y-axis. We always want to put the x-axis horizontal and the y-axis vertical. This way, the formulas that I derived for you during the lecture will work. Okay, those formulas were derived assuming that the x-axis was placed horizontally and the y-axis was placed vertically. Okay, you don't have to make that choice, but if you don't make that choice, then those equations don't work. You'd have to rederive them. It would be a mess. So for all intents and purposes, we're going to just always stick to the fact, to the convention that the x-axis, whoops, hold on here. The x-axis is horizontal like that. Okay, so there's the plus x-axis like that. And the y-axis is, oh, let me draw like this, is vertical like that. All right, one more time. There we go. Okay, there's the y-axis like that. All right. And you need to say where is the thing at t equals 0, because when you say initial, initial means where is it at t equals 0. Again, you could choose it anywhere, but I think, it makes perfect sense to choose this point right here as t equals 0 like that. All right. Okay, so you need both x and y axes, because in 2D, like I'm going to draw a point here and I'll erase it in a minute, but if I said to you, like, where is that dot there in the plane, one number would not be enough. If you just give me x, well, then all you're really saying is, like, how far horizontally would you move so that you're underneath it. Okay, so if you're here at the origin, how far would you have to move horizontally so that you're underneath it? But that doesn't tell you how high it is. Okay, and if I give you the y, well, that tells you how high it is, but it wouldn't tell you how far you'd have to travel horizontally before you get underneath it. So you definitely need both numbers. Okay, and let's go ahead and start looking at the initial and final. And I forgot, by the way, I should read what I'm asking you to calculate. Let me switch back to the other screen. I mean, I described here that you're at the bottom of, you're at ground level, and you throw it and it lands on the top of a hill. But what are you asking? And there's actually two sets of questions here. A and B go together, and they're asking how long does it take before it reaches maximum height, and what is the maximum height achieved? Okay, and then C, D, and E talk about not maximum height, but when it actually lands on the top of a hill. Okay, so how long until it reaches maximum height, and what is the maximum height achieved? So there's going to be an initial and a final. The initial is like, where does it start, and that's obviously at t equals 0 here when I release it. But the final is actually not when it lands on the top of the hill. It's at maximum height here like that. Let me do that in red here like that. Okay, now the word final is kind of a funny word. I mean, obviously the motion continues past that point there, the maximum height. But, like every physics textbook uses the term initial and final. And all it really means is the point after some time t at the point at which you're of interest, okay? And so even though it doesn't, don't think of the word final as it stops there, okay? It's just that that's the point at which we're interested in. So the motion that we're interested in starts here when I toss it. I guess I could put a little red dot there. That's the initial where it starts, and then the final portion of the motion that I'm interested in is when it gets to maximum height. Okay, and so let's go through, and now the third step is to read off the values of those 2 points, and both their positions and velocity. So initial position, initial velocity, final velocity. Okay, so the initial velocity, the initial position is down here at the origin, and it's 2 numbers, because position is a vector. And so there they are. This is initial x component of the position and initial y component of the position. Okay, I'll put a little bracket there like that to say that those two go together. Okay, they go together to form the initial position, and it's at the origin because we constructed it such that the origin was at that point. And so obviously x is 0, and whoops, and y is also 0. All right, so there you go. There's our initial position. Let me see if there's any questions in the chat. All right, no questions so far. All right, so do this systematically. Initial position. The next one is the final position, and that's also an x and y value. Okay, and we'll just write x and y without the little knot, without the little o there. Okay, x is equal to and y is equal to. So now we're looking at that point right up there. Okay, and you say, well, what's its x? And the x would be like if I drew a projection down here all the way down to the x-axis. What would I read off of the x-axis? And the thing is that you can reread the word problem, and there just isn't that information. That information isn't there. Okay, so question mark. We don't know how far it travels horizontally. until it gets to the maximum height. And same thing if I were to draw the vertical here. I won't extend it all the way across, but you go all the way across with the vertical. Y, you also don't know that. And in fact, that's one of the things that you're trying to solve for, because I ask what is the maximum height. So as far as the final positions goes, you don't know either the x component or the y component. Sometimes you'll know one, sometimes you'll know the other, sometimes you'll know both, but in this case, you don't know either of them. Okay, so all right, so we got initial position, we've got the final position. Next one is the initial velocity. All right, and last week we spent well, basically the whole week just on vectors. It was kind of a short week, and for vectors, the big thing was converting between Cartesian and polar. And the reason is that all of the equations here are in Cartesian, okay? The polar version of these equations are just very, very messy. And so, I gave you gave you the equations in Cartesian, but you may be given the information in the problem in polar, and then you have to convert to Cartesian. And that's exactly what the situation is with the initial velocity. So let me read the problem again. You can't see it there, but just let me read the part of the problem. I say I toss the ball with a velocity of 25 meters per second at 60 degrees above the horizon. Okay, so 25 meters per second, 60 degrees, that is magnitude and direction. So magnitude and direction, that's polar. All right, so let me try to draw that in here. And so I'm going to draw the initial velocity in green. And the initial velocity, of course, would be along the path like that. All right. Of course, it starts to curve, but I'm just going to draw it like that. All right. And so there's the initial velocity vector, and it has a magnitude of 25 meters per second. Okay. So magnitude just means, you're going to hear me use that word a lot. Okay. Magnitude just means how fast is it going? I don't care about the direction. Okay, so just how fast is it going irrespective of the direction. It's not its x component, it's not its y component, it's the full velocity, but not the direction information. Okay, and the other piece of information I say is 60 degrees above the horizon. So horizon, I know there's a hill here, but if you're standing at ground level and you look out to where the sky meets the earth at a far distance, that's your horizon. And that would actually define, your x-axis. So the x-axis is basically the line of sight from where I'm standing out to the horizon, okay? And so I'm measuring actually from that x-axis to the vector like that, and that's my angle theta, and that's 60 degrees, and that's exactly theta, okay? So I give you the magnitude, I give you the angle, and that defines the vector, okay? But you can't use those. What you need are the x and y components of the initial velocity. And I don't have enough room to do all the math here, and it's also kind of annoying to use the whiteboard to do it. But I can write at least the formula. You want v naught x and v naught y. Okay? And I'll even draw them in a minute down here to show you what they mean. Okay? So v naught x is the x component of the initial velocity, and v naught y is the y component of the initial velocity. And when I showed you this on the lecture on polar, I did r cosine theta, and there was that r that was the magnitude, but I was kind of implicitly thinking of the vector as a position vector, but it applies just as well to a velocity vector. Okay, so so the magnitude, so that r basically is the magnitude of the vector. In this case, it's going to be 25. I'm just going to write v naught, and I'll do the math on the in the text editor. V naught cos theta like this. So this is the general formula. And the y component is v naught sine theta. Okay, like that. All right. So what they correspond to, and maybe I can draw that in purple here. Like if I take this green vector here and I just break it up into an x component here. So here's the x component like that. That's your v naught x this way. And you do the same thing. You break that vector up and you get its y component. That's like that. Okay. And that's your v naught y. I don't have room to write it in there, but it's your v naught y. And v naught x and v naught y are basically telling you how fast. I mean, the vectors, the green vector is at an angle. So it's both, you could say the thing is both going up and it's going to the right. And so the decomposition of the polar vector into its Cartesian says, well, to how much is it traveling to the right and how much is it traveling up, at least initially, okay? And so that's what v naught x is kind of a measure of, like, how fast is it moving along the x-axis, okay? And v naught y is like how fast is it moving along the y-axis. And if you have a little bit of difficulties picturing that, let me actually get rid of that purple there because it's going to start to get messy. If you're having difficulties picturing that, let's assume that we have the ball at some other point here. Like, I don't know, I'll just pick this point right here, okay? And, like, imagine the sun is directly overhead. I mean, that doesn't happen on this part of the world, but like if you're at the equator during the summer solstice, the sun is directly overhead, okay? And it would project a shadow, and I'm going to project it all the way down here to the ground level, okay? And this is where the shadow would be, okay? So as the ball moves, because this ball is going to be moving that way, as that ball moves, the shadow is going to move, okay? But the shadow is going to move along the ground like that, okay? And v naught x is basically the velocity at which that shadow moves along the ground, okay? So as this thing is moving, it's how fast does the shadow move along the ground, okay? Now, v naught y is the same thing, but you would have to project it onto the y-axis. You'd have to have light going the other way, but I think you've got the idea, okay? So it's basically, you could think of the v naught x and the v naught y as they're called a projection. You can think of them as a shadow, okay? So v naught x is like how fast would this shadow be moving? Not the ball itself, not how fast is the ball going, but how fast is its shadow along the ground move. Okay, so let me get rid of that. And that's physically what is meant by v naught x and v naught y. Okay, so let me see if you have any questions. So if there are no questions about the diagram so far, what I'm going to do now is I'm going to switch to the other my text editor. We're not quite done. I mean, because we have to still work out what the initial velocity is. There's also the final velocity, but I'll do that on the other screen. Okay, so over here, let me just, I've already got these numbers written down, so I'm just going to cut and paste. I'm just going to cut and paste the numbers that we would get off of that diagram. So this is like step 3 of the diagram. It's the transitional step between the diagram and actually, plugging into the equations. Okay, so just to repeat, this was our initial position, those two numbers. It starts at the origin, so x naught is 0, y naught is 0, okay? This was the final position, okay, x and y, and we didn't know either of them, and in fact, y is what we want to solve for. I should say solve for this in part B, okay, because part B asks for the maximum height, okay? And here's where we were. This was our initial velocity and converted to Cartesian, okay? And so the formula for v naught x is v naught cosine theta, and that's 25, because that's the magnitude of the velocity. See here where I say it's traveling with a velocity of 25 meters per second, so there's your magnitude, multiplied by cosine of the angle, okay, and that turns out to be 12.5. By the way, cosine of 60 degrees is one of these values that you should memorize. Cosine of 60 degrees is a half. Sine of 30 degrees is a half, okay? And so you'll see sine of 30 and cosine of 60 quite often, okay? And they're both equal to a half, okay? So 25 cos 60 is 12.5, and 25 sine 60 is 21.7. All right. Now, I didn't actually show you the final velocity. That would be the velocity at the very top. And here's what the values are, but let me go through them and explain what's going on. Vx and v naught x are always the same, okay? And I should probably here put meters per second, all right? Now, why are Vx and v naught x always the same? And that's because the acceleration is straight down, okay? So one of the reasons for, the reason that simplifies the equations is by choosing the x-axis horizontally and the y-axis vertically, the acceleration is purely in the y direction. There is no acceleration in the x direction, okay? If there were an acceleration in the x direction with our choice of the directions for x and y, if I drop something, if there was some acceleration like that way, then, the object wouldn't fall down, it'd fall to the right a bit. It'd fall down and to the right, or it'd be falling down and to the left, and that would be a very strange world, okay? And so there's no ax, there's no acceleration to the right or to the left. The acceleration is purely along the y direction, purely down. So what does that mean in terms of velocity? If ax is 0, it means that vx doesn't change. Whatever its initial value is, it's the same value all the way along. That shadow that I drew a minute ago, it would travel along the ground at the same speed, okay, all the way along. And so if the initial velocity is 12.5 meters per second, the final velocity at the very top there at maximum height is also 12.5 meters per second. Okay, so that tells you what's going on with that one. But then what about this Vy? Why is that 0? So this is like what we had in 1D kinematics when I threw something up and I wanted to get the maximum height. It got to the maximum height. When it gets to the maximum height, it has to temporarily stop. And the reason is that it's going up before, it stops, and then it's coming down. Up is positive, so the velocity is positive before it gets to maximum height. It's negative after it gets to maximum height, and at exactly at maximum height, the velocity is 0. Okay? But it's not the full velocity, it's just the y component of the velocity, because the y component of the velocity is the velocity going up and down. Okay, it's just that part that you're looking at that talks about how fast are you going up and how fast you're going down, irrespective of traveling horizontally. Okay? And so in a sense, this is really what defines maximum height right there. Maximum height occurs not when your velocity is 0, but when the y component of the velocity is 0. Okay? And so, like you could take that almost as a definition. All right? You could say whenever you see a problem and it says at maximum height, Vy is equal to 0. And then proceed like that. All right. And so that's how we got that one. So in this case, we know both the x and y component of the final velocity. All right. And now the acceleration, ay, is straight down. Okay, it's straight down, and that's in the negative y direction. So there's no ax. I didn't write ax is equal to 0, but you could write that. It's just not necessary. It's not part of the equations. So ay is negative 9.8, but in this course, we're rounding it off to negative 10. So negative 10 meters per second squared. And we also don't know the time it takes to get to the top. Okay, so that's also a question mark. I mean, you just reread the problem, and by question mark, I mean nowhere in the problem, in the word problem, do I tell you. Okay, so you just don't know when you start off. In fact, this is what you're trying to solve, what you're solving for in part A. Okay, which is what we're working on right now. So there it is, and you've got that all done. Now, the tests and the assignments, they're multiple choice, and you could say, well, you know what, I'm just going to jump right to the questions, and probably not a good idea. I'm going to have a problem like this, at least one problem like this on the test, and it's going to be one setup, but it's going to have multiple questions about that same setup. So it is worth investing the time to make sure that you get these values correct, because if you get these values incorrect, then everything after that goes wrong. Okay, and so there we have it, and then now we're ready to plug into the equation. So I'm just going to cut and paste all the way down to the solution here. It's fairly straightforward, but let me do this. I find that by cutting and pasting, I tend not to make as many errors. Okay, so these are the 4 equations that govern constant acceleration, 2D. Okay, the first one is the height as a function of time. So y, you can think of it as the height. Okay, so whatever the y value is, it's how high you are above the ground, and it's as a function of time. And of course, you need ay and v naught y and y naught to be able to solve for that. Okay, but it's basically y as a function of time. Number 2 is vy as a function of time. Okay, and number 3 is actually equations 1 and 2 with the time eliminated. And number 4 is the only equation that talks about horizontal motion. Okay, so 1, 2, and 3 are about vertical motion, and equation number 4 is the horizontal motion. So you take a look and you say, well, I'm solving for time, so immediately equation number 3 is out because it's got no time in it. So you can't solve for time if the equation doesn't have time in it. Okay, you might look at number 4 because it's pretty easy, but you don't have enough information because you don't know what x is. Okay, and you don't know what t is. So there are 2 unknowns in number 4, and so that's no good. And number 1, could you use number 1? Probably. Let me see here. Do you know why not? V not y, a y. You don't know y, and you don't know t. So number 1 you can't use. You have to use number 2. You have to use number 2. Okay, and it's also fairly one of the easy ones. Okay, so we're going to use number 2 to get the time. All right. And there it is, just repeat it again. Okay, And what you do now is just substitute in Vy is 0, Ay is -10, V naught y was 21.7. That's a trivial equation to solve for, and you get 2.17. Okay, so that's the time it takes to get to maximum height. All right, let me see if there's any questions about that. All right, I'm not seeing any questions in the chat, and so I'll continue. And also let me know if I'm going too fast. I mean, I do the cut and paste, but I don't want the cut and paste is more like so that I don't make errors or I don't waste your time like fixing my typos or whatever. But I don't want to go too fast. Okay, and the whole point of this is to do it interactively, so to give you an opportunity to ask questions while we practice it together. Okay, so all right, we got that time, and now let's look at the next question. What is the maximum height achieved? So when you see these questions, like what is it asking for? Maximum height. Well, what is that in these equations? Like what variable does that correspond to? And I just said it actually. Height is y. Okay, and so your equation has to have y in it, and that's either equation number 1 or number 3. Okay, now we know the time, so we could use equation number 1, but I think I used equation number 3. You could use either 1 or 3. Okay, and let me see, which one did I use? Yeah, I did use number 3. Okay, and again, there's no reason you have to use 3. Number 1 will also do it. Okay, this happens a lot. Like the first question that you answer usually is, there's only one possibility because your values are restricted. But as you start to get more values, then you have different ways that you can approach it, and then that happens. They better be consistent. Okay, so as I say here, you can use either equation 1 or 3. I said let's use number 3. And number 3 is basically Vy squared is equal to V naught y squared plus 2ay y minus y naught. Okay, Vy is 0. V naught y we found was 21.7. There's a bit of a round off there, by the way, if you're doing it at your end. Okay, and 2 times ay is negative 10. Okay, and y minus y naught is 0. Okay, and I think I might have gone a little bit too fast on that. Let me show you what you would get here. 0 is equal to, and what's 21.7 squared? It is this number right here, minus, so 2 times negative 10 is minus 20, and then y like that. Okay, so that's basically simplifying this. We get that, and then bring the minus 20 to the other side, divide by 20, and you get that. Okay, so there you go. There's the maximum height. Okay, you'll notice that the hill was 20 meters high and the maximum height is 23.5 meters. That better be the case, otherwise you wouldn't you wouldn't throw it hard enough to get to the top of the hill. Okay, and if that did happen, then obviously I've made a mistake, and of course I will endeavor not to do that. All right, so that answers the two questions, which is like how long does it take to get the maximum height, and what is the maximum height. All right, let me see if there's any questions. All right, everyone sounds like everyone is doing okay. Okay. All right. Okay, let's go on to the next one. The next three problems. They go together. Okay, they go together. So how long before it lands on the top of the hill? And how far did it travel horizontally before landing? And then what's the velocity just before it lands? Now, I did something here, like, I don't mean to be tricky, but it's a little bit tricky here. Whenever there's a change in either your initial or your final positions, you have to rethink everything, okay? Not that you necessarily have to redraw the diagram and everything, but you really need to rethink it, okay? And the reason is that your initial is the same. I'm still at ground level, when I toss it. But now that final is not at maximum height. The final now is when it lands on the top of the hill. And so that means that your final values are going to change. They're not going to be the same. So watch out for that. Okay, so remember, like if any of your final positions or velocities change, you better rethink the problem. So let's go back to the whiteboard here, and let's rethink it. Okay, and I'll do this in, I guess, purple. Okay, and the red dot here, that red dot, that was for parts A and B. That was for maximum height. So that's where the final is maximum height. But now for parts C, D, and E, maximum height, the final is right there. Okay, it's like where the ball hits the top of the hill. Okay, and if you look at the numbers, if you go through them, each one, you'll see that all the finals change. So if you take a look here, you say, well, what's the initial position? Well, the initial position is still here. I'll redraw it in purple like that, okay? So the initial is the same as previously. So X naught and Y naught, they're the same. Nothing changed there. Okay, they're fine. But now the final is not up here. The final is there. And so let's see if these values still make sense, okay? So actually, let me put a cross through them, and we'll just do them again. So X is equal to, and let's take a look. So X is how far you move this way along the x-axis like that, okay? And if you read the problem or whatever, you don't know. In fact, that's one of the questions, like, how far did it travel horizontally? So you don't know that value, okay? So that's a question mark, all right? It did change, but and they're unknown, but they're different unknowns. Like this unknown here is going to be different than that unknown, because this unknown corresponds to like that value right there. See, I'll just draw, whoops, just draw a projection very quickly like that. That x value would be to there, whereas this x value here is to there. So, you might have an x value. They're both unknown, but they're two different unknowns, okay? And then the y value here, that one we actually do know this time, okay? And that's because it's at the top of the hill. So if I were to project that over here to the y-axis, sorry, I didn't quite draw a straight line, but I move over here to the y-axis, that's the height of the hill. And the height of the hill was, you can read from the problem, 20 meters. So we do know that, okay? The initial velocity, they're the same. So these are just the formulas, but they'll remain the same, okay? And the final velocities, they're going to change. But let me do that in the other screen, okay, like that. All right. So let me just cut and paste the values from my answer sheet here. Like that. And you'll see here I start off by saying reanalyze the diagram. Whoops. Now you can see it. So reanalyze the diagram because the final position and velocity has changed, or have changed, okay? The initial is still the same. So since the initial are still the same, there's the initial position, that remains the same, okay? And there's the initial velocity, that remains the same, okay? But the final position, that one right there, has changed. X is unknown, but Y we do know now. It's the top of the hill. It's the height of the top of the hill, which is 20 meters. Okay, and what about the final velocity? Well, there we have this situation. The Vx is still 12.5 because Vx doesn't change. Okay, it remains the same all the way along. There's no acceleration in the x direction, so it doesn't change. Okay, Vy is a question mark, and the reason is that here before we said that Vy at maximum height was 0, okay? But now we're not at maximum height, so Vy is not equal to 0. Now, it's important that you think about this problem right. In fact, I even worded it suggestively. I said just before it hits the ground, okay? So just before it hits the ground. And the reason I did that is because when it hits the ground, those equations don't they're not really valid anymore. The reason they're not valid is because as soon as the ground is involved, the acceleration is not just an acceleration due to the gravity, it's also the acceleration of the interaction with the ground. And you can imagine how complicated that motion is. Then the ball hits the ground and it bounces, or maybe it embeds itself. Who knows what happens, okay? So don't say that the velocity is 0, because that, if you say Vy is equal to 0, you're saying you're at maximum height, and that's not what's going on. The ball is traveling in the downwards direction. It's actually at an angle, but it's got a downwards movement. So at best, you can say that this velocity is negative. You know that much. But you don't know its value, okay? You don't know the value of Vy, all right? And it has to be negative. I think everyone would agree that just before it hits the ground, it is moving downwards. It's got a negative velocity, okay? So that's what's going on there. Ay is the acceleration due to gravity, and it's downwards negative 10 meters per second squared, like we did used above. And the time is also unknown in this case. And once again, this unknown time is different than the unknown time you had up here, okay? So one of the things you have to be careful of, because things changed, don't just grab numbers that you've already solved for and then use them again. So if you had put here like t is equal to 2.17, that would be wrong. okay? Because that would correspond to the time when you reach at maximum height, and don't confuse that time with the time when you hit the top of the hill, okay? So that's question mark. And there you go. There are all the values read from the diagram. So I wanted to do it in this order because I really wanted to emphasize that when I start moving around initial and finals, you really have to rethink these values, okay? It's not a lot of work. I'm spending a lot of time explaining this, but it takes a minute, but do rethink them. Okay, do rethink them. Just reread them off of the diagram. All right. See if there's any questions before I just actually solve. All right, I don't see any questions, so I just assume that no questions. I can continue here. Okay. And what are we asking for? So it says here, how long before it lands on the top of the hill? And you take a look at the numbers that you have. Okay, you're obviously trying to solve for time. You go back to the equations that I've given you and you say, well, what do I know? What do I not know? Okay, so you're solving for time, so it's either 1, 2, or 4. Well, 4 you can't use because it's horizontal information, and that you don't have x. Okay, you don't know how far x is, and so you can't solve for t because then there are two unknowns. Okay, number 2 doesn't work because you don't know vy. All right. It worked before because we knew Vy was 0, but not now. And so you have to use number 1. Number 3 you can't use because there's no time in it at all and you're trying to solve for time. So you have to use number 1, and guess what? You cannot avoid the quadratic. Okay. So I'm just going to cut and paste the solution here. It's a little bit long, but just cut and paste the whole thing and we'll go through it. All right. So use number 1 to find t. Okay, so how did I conclude that? By process of elimination. Okay, so there's equation number 1. Y is equal to 1/2 ay t squared plus v naught yt plus y naught. Substitute in all the numbers you know. You know everything except for t. Okay, so y is 20, ay is -10, v naught y is 21.7, and y naught, that was the initially at ground level, that's 0, like that. And so you simplify this, so half times -10 is -5, and also I subtracted 20 from both sides and I get it into this form here like that. Okay, now that's a quadratic, and you could get the a, b, and c coefficients out of that. I have, since I first learned this, I mean, I can't remember how long ago that was. I guess, my high school days. I've always just divided out the a coefficient. The reason I like doing that is because it makes a 1 in the quadratic equation, and it just seems a little easier to solve. Okay, you don't have to do that, but that's my preference, so that's what I did here. So, here's -5, and -5 divided by -5 is 1. So the coefficient in front of the t squared becomes 1. Here's positive 21.7 divided by -5 is -4.34. And then -20 here divided by -5 is +4. And then looking at that one and identifying the coefficients, I've got 1. A is equal to 1, B is equal to -4.34, and C is equal to 4. Okay? And the quadratic equation looks a little funny in the text editor here, but I think you can read it. It's minus b plus or minus, because there's always two solutions with a quadratic, -b plus or minus the square root of b squared minus 4ac. All of that divided by 2a. Okay, and then substituting in the numbers. The only thing you have to be careful of is, like, the b is negative, so make sure you get all the negative signs right. So here you have negative, but b is negative too, so you get a negative 4.43. Okay, so you can see that negative is part of the formula, that negative is part of the value of b. All right, and then plus or minus the square root of b squared. When you square a negative number, it's going to turn out to be a positive number. So I've seen people make this mistake on a calculator. They'll do negative and then 4.3 and then they'll square, but the square will only apply to the 4.3 and not to the negative, and so that's a problem. And you'll get a negative number from that, and that's obviously wrong. Whenever you take a negative number squared, it's a positive number because a negative times a negative is a positive. I'm sure you've seen that before, but it just bears repeating. And then here's minus 4 times c, a being 1, and there's 2a where a is 1. Okay, and working it through, it just turns out that those are the two values you get. You get 3.01 seconds and 1.33 seconds, like that. Okay, now our tests are going to be open book, as you know, and So you could use your calculator, like a lot of programmable calculators will have the quadratic formula in them. Or if you like, you could just use this site here, okay, math.com. Math.com has a lot of good formulas in it. It's mostly things at the level of high school, like trig functions and things like that, or trig identities and things like that. I mean, but they're still pretty good, because if you forget them, I sometimes forget really complicated trig identities. I'll look them up here, okay? And that's kind of a long URL to remember, but what you could do is just go to Google and just type in solve quadratic equation online. And you'll get all these sites, including this one, but you'll get a bunch of other sites because it's pretty easy to create a website for. You just put in the A, B, and C coefficient, you press a button, and they'll give you the two values, okay? Now, you've got two numbers there, and two times, and usually one of the times positive, the other one's negative, and you go, oh, I'll choose the positive time. But this time they both turned out to be positive. And you say, well, how do I decide? And you can see here the answer is see the diagram for why you want the 3 seconds. So let's switch back to the diagram and see if we can make sense of why we got two values. Okay, so let me draw a horizontal line here from the like this, a horizontal line there like that. Okay. And that horizontal line there will cut the y-axis at 20 meters. Why? Because the height of the hill is 20 meters, okay? Now, when we used equation number 1, that is y is a function of time, okay, that's the height as a function of time, we basically asked at what time is this thing at 20 meters height? And the answer is twice. It's at 20 meters height twice. It's at 20 meters height on the way up, right there, okay? And it's at 20 meters height on the way down there, okay? Notice that the purple line cuts the black parabola at 2 points. It cuts it on the way up, like when the ball is on the way up, and again when it's on the way down, okay? So guess what times these are? Well, t equals 0 is at the origin, and obviously this one comes on the way up, comes before on the way down, okay? So this one is at time t equals 1.33 seconds. So that's t equals 1.33 seconds. Okay. And this one is going to be at 3.01 seconds. All right. And it's pretty obvious that since it's landing on the top of the hill, you have to choose the 3.01. Okay. So that's how you choose. Now, before I switch back, I do want to show you something. And unfortunately, I can see that I didn't really draw this symmetrically. But remember the time that we got when it was at maximum height here? The time we got up there was 2.17 seconds. Okay. Now, the parabola is totally symmetrical. So that 2.17 seconds, it's exactly in the middle of the 1.33 and the 3.0 seconds, okay? It's right in the middle of the two. In other words, the time it takes to go from the 20 meter mark on the way up to maximum height, I'm going to try to draw that in purple here. That time, it turns out that time is 0.84 seconds, like that. Okay, I'll show you how I got that in a second, okay? That time there, it's exactly the same as the time it takes to go from maximum height back down to 20 meters. Okay, it's like that. That's also 0.84 seconds. And that's because, as the thing goes up, it comes down in the same way that it went up, okay? In other words, the parabola is totally symmetrical around the red dot there, okay? Mine isn't because I didn't draw it so well, but that's the idea, all right? So if I switch back, I'll show you how I got that 0.84 seconds. So over here, you could say, by the way, maximum height is obtained at 2.17 seconds. Notice that 3.0 seconds, that could be written as 2.17 plus 0.84, and I got the 0.84 by just subtracting 3.01 minus 2.17. Okay, so the 3 second can be written as the middle plus 0.84, and the 1.33 can be written as the middle time minus the 0.84. 8, 4. Okay, and so that's what these two solutions mean. Okay, so I know I didn't ask you about this, but I wanted, since we were here, I wanted to show you this because it reinforces how the whole thing works. All right, let me look in the chat here. All right, a few people dropped out, but I don't see any questions. The rest of this is pretty quick. Okay, so the parabola, I mean the quadratic is mostly where all the problem is. All right, how far did it travel horizontally? Well, as soon as you hear horizontally, you have to use equation number 4, and equation number 4 is really trivial. It's just that x is equal to v naught xt plus x naught. Okay, and the time you want to use is obviously the time until it gets to the uh, to the top of the hill. That is the 3.10 seconds, and so you just plug in and you get 37.6 meters. Okay, so that's how far it travels horizontally before it lands on the top of the hill. Not very deep. Okay, I mean the hard part was getting the time. Once you got the time, the problem unraveled. And then the last question here is what is the velocity just before it hits the top of the hill? Okay, what's the velocity? And I say just give me the magnitude. Now, the velocity is a vector. So that velocity just before it hits the top of the hill is a vector, and it's got an x and a y component. All right, so we're going to need vx and vy right there just before it hits the top of the hill. In other words, vy is not 0. Don't make that error. Okay, but I'm not asking for vx and vy. I'm asking for the magnitude. And so whenever you hear magnitude and angle, or magnitude and direction, give me the magnitude and direction, polar. Okay, and whenever you hear give me the components, give me the x and y components, give me the x value, the y value, that's Cartesian. Okay, the equations work in Cartesian, and so you're going to get vx and vy first, and then once you have vx and vy, you're going to convert to polar. I didn't even ask you for the angle, but just the magnitude, but there it is. Okay, you still need vx and vy even for the magnitude. All right, so let me just cut and paste that. It's pretty straightforward to do that. Okay, and so where is it here? Oops. Okay, so I start off by saying we want both Vx and Vy. Okay, and Vx we already know. It's constant all the way through the motion. It's 12.5 meters per second. Okay, Vy we don't know. You could probably use equation. I guess you could have used equation 2. No, you have to use equation 3. Okay, so we're going to use equation number 3 here. All right, and so you got vy squared is equal to v naught y squared plus 2ay y minus y naught. Okay, and so there's vy squared there, and that's unknown. You don't know vy, and v naught y we found to be 21.7. Ay was negative 10. Y was 20, y naught was 0. Okay, and so simplifying that, we get that vy squared is equal to 70.89. All right, now right there, that one, most people, what you'll do is you'll put that number in your calculator, and then you'll hit the square root, and the calculator will just give you 8.42, like that. Okay, and that is correct, but it's the square, and so you need to consider both the positive and the negative solution. So remember that when you have like something like z squared like this is equal to 4, there's two possible solutions. Z could be equal to 2, but you could also have that z is equal to negative 2, because negative 2 times negative 2 is also 4. And so here I've got the vy is equal to plus or minus 8.42. Okay, because there's two possible solutions when you take that square root. Okay, both of them, when you square them, will give you the 70.89. And you say, well, which one do you want? Well, you actually want the negative solution. Okay, so this is a case where if you hadn't considered both the positive and negative, you would have gotten it wrong. Okay, and the reason you want the negative solution is because when it lands on the top of the hill, it's coming down. Okay, it comes down, and so the y component of the velocity has to be negative. All right, and not that it matters for the magnitude, but it would matter if I'd asked about the direction. Okay, if you're taking the positive, it would give you a vector in the first quadrant going upwards, and that's wrong. That's on the way up, but on the way down, the vector's pointing into the fourth quadrant. Okay, so you get the direction wrong if you didn't use the if you didn't use the negative instead of the positive. Okay, so just be careful about that. Even when you just take the square root of something, your calculator will give you a positive number. You want to consider both. Okay, so all right, now that we have both Vx and Vy there, you say, well, what do I do with that? Well, we want the magnitude. The magnitude is like R in the lectures on vectors, and so that's the square root of the x component squared plus the y component squared. Okay, that's what we mean by magnitude right there. Okay, and so just plugging in, you get the answer. And the only thing again to be careful of is that when you square the negative 8.42, square both. I mean, square the negative along with it, and so that's actually because negative 8 point, a negative number times a negative number is a positive number. Okay, so just make sure you have that negative in there, and the answer turns out to be 15.1. Okay. So there it is. That answers that one. Let me see if there's, we're running out of time. So let me see if there's any questions in the chat. No, I lost a few more people here. Okay, let me just quickly tell you what you should do on your own. So repeat this problem on your own. Okay, repeat the problem on your own. Well, repeat it first the way I did it and just see if you can get the answer right. But also repeat it, but this time, instead of a hill, just make sure that the ball lands at ground level. So do the whole thing again, but the ball lands at ground level. And also repeat the whole thing, but this time, rather than you being at the bottom of the hill, you're at the top of the hill, throwing down. Okay, so so assume that you're at the top of a hill 20 meters high, and then it lands on ground levels. So then you've done all three possibilities. Leaves ground level and it lands on the top of the hill. The other one is it leaves ground level and it reaches ground level, and the other one it's from the top of the hill and it goes down to the bottom of the hill. And those are the three possibilities. Okay, and I'm not going to give you the solutions to those, but if you have questions, if you have difficulties, that's what the office hours are for. Okay, and then also on the weekend, I'm going to give you at least one problem like this to solve, and this way you'll have more than enough practice. All right, so very quickly, let's do the last one here. It doesn't take long. I'm riding a bicycle around a corner with 7 meters radius. The fastest I can turn is without slipping is about a quarter of the acceleration due to gravity. Okay, that's the most acceleration before I start to slip. So it's a quarter of g, a quarter of the acceleration due to gravity. How fast can I go around the turn safely? Okay, so whenever I say how fast, it means velocity. All right, this really is easy. You don't need a diagram. Let me just cut and paste the solution here. All right, so here we go. So the radius is 7 meters. Okay, because I tell you that. All right. The acceleration, I said it's 1/4 of the acceleration due to gravity. So that's like 0.25, 25% of 10, which is 2.5. Okay. And now you just have to choose the equation to solve for V. There are the three equations. They should be in your notes from the pre-recorded lecture. V can be written as 2 pi r over capital T, where capital T is the period. It gives you V, but you can't use that one because you don't know the period. That is the time for one complete revolution. I don't give you any time information, so you can't use that one. The second one is the acceleration, also in terms of R and T. Okay, and we don't want to calculate the acceleration, and again, we don't know T, so can't use that one. It's the third one that we're going to use, and we can't use it in that form because we want to solve for R, so just isolate R. Okay, and then solve, and then plug in the numbers. Okay, so just multiply both sides by R, and then take the square root, and you find that V is equal to the square root of A times R. A is 2.5 meters per second squared, R was 7, and it turns out to be 4.18 meters per second, okay? Approximately 15 kilometers or 10 miles per hour, okay? Which kind of makes sense if you're going around a corner, which is like a 20 foot radius or 21 foot radius, okay? And, you want to do it safely. 10 miles an hour sounds about right. If you try to turn faster than that, you're risking it a little bit, okay? So this is on a bike, obviously. All right, so like there are variations on this, but it's kind of hard to do a lot with just these three equations. Okay, there's only 4 quantities there that are at play: R, V, and A, and then the period. Okay, and there's no directions associated with this because the directions are always fixed in the sense that the acceleration is always towards the center, centripetal, and the velocity is always tangential to the outside. Okay, so there it is. That's the last problem, and I didn't give you any practice problems with that. You will see some on the assignment for next week. Okay, let me see if there's any questions in the chat, and if not, then we're done. So is everyone good? And that's my dog barking. If you can hear him in the background, the mailman just delivered something. So is everyone good? Do you have any questions? Otherwise, we'll just end the stream. All right, we're looking good. Thank you, guys. And so, all right, have a good weekend.